Okay, let's work on proving that the power set of the empty set is what we expect it to be. So what do we expect it to be? Let's build up a guess. So how do we think about the empty set? I imagine that it's just an empty bag. It's just the bag, the material that makes up the bag, and there's nothing inside it. Then what's the power set? Well, the power set of a bag is going to be a bag of bags, right? So it's a large bag containing possibly many bags, where each bag inside it is going to be a subset of this bag. So the question is, what are the subsets of the empty set? So if you find one subset, then you can put it in here. Another subset, put it in here, and so on. How many subsets does the empty set have? Well, the empty set is a subset of itself. Like, this is true. There are two reasons for that, actually. One reason is this idea in Theorem 13, the minimality of the empty set, that it is a subset of any given set. So the empty set is a subset of anything, including itself. And another reason is the idea that inclusion is reflexive. The subset relationship is reflexive, so anything is a subset of itself. Okay, so we have very good reasons for believing that the empty set is a subset of itself. And so, what do we expect to find in this bag of subsets of the empty set? We expect to find the empty set itself. So our empty bag would be in here. And remember, when we're doing set theory, the structure of these bags, or whatever container, boxes, whatever you're imagining is the container, the structure of the container matters. So be careful not to just collapse things. So I've seen people sort of imagine this situation, which is this, a bag containing an empty bag, and then be like, well, it's all empty in the end, so therefore it's the same thing as this. But we have proven in a past video that that's not true, that they're different, right? So make sure you maintain the structure of the containers and who contains whom, rather than just collapsing everything and only focusing on what's inside the innermost bags. Alright, so we have ourselves a pretty good conjecture, which is that the power set of the empty set is singleton empty set. So it's not an empty set. It's a set that has one element, and that element is the empty set. Let's prove this. So nothing here is a proof. This is all just conjecture. So let's upgrade this guess to a theorem, where the only difference between a guess and a theorem is that a theorem is followed by a proof. So that means we have to try to prove this. Now, the kind of thing that we're proving is an equality. To prove this, so I'm trying to prove an equality, so that means probably axiom 8 might get involved, or more likely, Theorem 10 would get involved. And what are we trying to prove an equality between? Well, a certain power set construction and a certain singleton construction. So that tells you, before we even get started, you already know what is likely to come up, what tools you're likely to need. So good, before you start the proof, it would be good to just go and review those tools so you're aware of what you're going to need. So here we are getting equipped. First, I'll go find the definition of power set, since that's involved on the left-hand side. I cannot get anywhere without the definitions, so I must look at this, take it in, interpret it in the particular context that I'm in. So I'm not looking at power set X, I'm looking at power set of the empty set. So I need to keep in mind what the definition of power set says that is. And the second thing that is involved seems to be a singleton. This is a singleton of something. So I'll go and I will look for the definition of singleton. That's back here. And then I'll have to interpret this in the context that I'm in. I don't have singleton X, I have singleton of the empty set. So interpreting those two definitions that I pointed out, that should be part of the scratch work. So I'm going to put it down here. The reason I put this as part of the scratch work rather than putting it in the proof is that you can assume that the reader of the proof knows all the definitions. So this is when you're using a theorem, it's good to tell the reader which theorem you're using. This is by Theorem 27 or whatever. But a definition, you can assume the reader knows all the definitions. You don't have to explain the definition. So in our scratch work, we explain it to ourselves. Okay, so power set of the empty set, that is copying over from the definition of power set, except with the empty set in place of x. It's the set of y's, such that y is a subset of the empty set. And what about the right-hand side, singleton empty set? That is just copying over from the definition of singleton. It's the set of y's that equal the empty set. That equal whatever is in here, which is the empty set. So this is the set of subsets of the empty set. This is the set of things that are the empty set, that are equal to the empty set. Okay, now I'm proving inequality, so I'm going to use Theorem 10. That means the proof splits into two parts immediately, which is really nice because each individual part provides me with assumptions that I can work with. That's why I like this more than Axiom 8. So like here, I would say consider any, and then I can just choose any unused letter. I'll use z. Consider any z in the power set of the empty set. And then hopefully I can prove that z is an element of the right-hand side. And here I would say consider any z in there. Now, I really should be using a new letter that I haven't used before, so maybe I should say consider any w in there or something like that. But it is understood, as long as I separate these two paragraphs with enough of a gap, of a vertical gap, it is understood that the z being talked about in this paragraph is going to be different from the z down here. So it's okay to use the same letter as long as you know that. Sort of once you're done with this half of the proof here, there's a reset that happens, and variable z here is a new one. Okay, so let's see. Consider any z in there. Now I can interpret what this means. So z is in there. That means z satisfies the membership condition for power set. So then, I'm using Axiom 5. You see, everything in this course is just going to be using Axiom 5 over and over again. So z is in there means this thing holds with y replaced by z. So z is a subset of the empty set. Okay, now if I have something which is a subset of the empty set, now what's my goal? My goal is to prove that z is in here, right? So that means my goal, just writing that in my scratch work zone, my goal is to prove z is in here, meaning z is equal to the empty set. So meaning this holds with z in place of y. So again, by Axiom 5, what I'm trying to prove is this, right? Z equals the empty set. So that's another equality that I'm going for. And I already have one of the two inclusions. So I could try to go for the other inclusion, but as you have seen before, trying to prove the empty set is a subset of z is a little bit awkward, and I don't really have to do it because I already have such a result. First of all, look right here. There's the other inclusion. In Theorem 13, the empty set is a subset of any given thing. So there it is. The empty set is a subset of z, and here I have z as a subset of the empty set. So z equals the empty set. But I don't even need to make that argument. That's done for me already in part 2 of Theorem 13. So if I reference this one says if z, I can put anything I want here, the free variable. If z is a subset of the empty set, then z equals the empty set. Wonderful. So by Theorem 13, part 2. By Theorem 13, part 2, z then equals the empty set. Anything that is a subset of the empty set must be the empty set. Great. And why was that my goal? Well, that's because Axiom 5 told me that that's what is needed to get z to be an element of this singleton. So thus z is an element of this. And notice I'm not saying by Axiom 5 anymore, right? Like I could have said, by Axiom 5 here, I could have said it here. I'm not saying it anymore because that's just such a common one that we really don't need to say that. I was only saying it early on since it was new to us. But yeah, once something becomes really, really common in your particular development, then you don't need to mention it every time you use it. All right, so let's see. I guess that finishes that inclusion, right? So now for this one, consider any z in there. Then, using the definition, which my face is covering, using the definition of this, that means this thing holds with z in place of y. So then z equals the empty set. And then my goal, so what's my new goal now, is to show that z is in here, which means I need this thing to hold with y replaced by z. So my goal is to prove that z is a subset of the empty set. Okay, great. Well, z equals the empty set. So z is a subset of the empty set. Now, where is that coming from? I know that is supposed to be obvious, right? But everything needs justification. Everything has to come from somewhere. If it's sufficiently obvious, then maybe I don't need to write the justification, but I still need to know it. If you don't know it, then it's not obvious, right? So what is the actual justification? It has to be something we can reference. See, I know this is like stupidly obvious, but pause the video and see if you can come up with an actual like theorem number. Like this is why we can go from z equals the empty set to z subset the empty set. Okay, now I'm going to give you what I think is the answer. So there are multiple answers, and I'm going to give you what I think it is, and I'm going to give you another alternative one, but there might be other ones. So I think that it comes from Theorem 7, Part 1, reflexivity. Things are subsets of themselves. Everything is a subset of itself. So if z is the empty set, well, since z is a subset of itself, since by Theorem 7, Part 1, z is a subset of itself, if z equals the empty set, then I can, by axiom 2, I can take that statement and replace the z by something that it's equal to, which is the empty set. So that's one way to get there. Another thing you could have referenced is Theorem 10. So Theorem 10 says when two things are equal, then it follows that both inclusions hold. That's actually what I just mentioned is probably how you would prove that direction of Theorem 10. So yeah, everything needs a justification. But this is a minor point for where we are now, right? Making the argument that I just described maybe would be showing too much detail. This is kind of a difficult, this is a challenge in Math 8, figuring out how much detail to show. What is too much detail? What do I need to write? When do I need to reference what I've used, and when is it okay to just use it and not mention it, assuming the reader knows it? So I would say that is pretty fuzzy, and that's not just in Math 8. That's in every math class, and in fact in mathematics as a whole. When you're writing for an audience, and you need to think about what it's going to take to convince that audience. So your goal is to convince people, right? Not just show off and try to look smart, but you want to convince. You want to not make it too difficult for people to read your proof. And how much detail you need to show, well, that depends on who it is that you are proving to. So what do you do in Math 8? Do you write as though you're writing to your professors? Do you write as though, I'm reading your proof and grading it, and you just write so that I understand what you meant? No, that's not the way to go. The goal in a course setting is actually to write as though your audience is your classmates. So if you think that your classmates currently at the level that they are now in the course would understand what you're writing and would become convinced by it, then that is a good level of detail. So that's the rule of thumb. Write for your classmates. All right, enough rambling. Where are we here? Are we finished? Almost. Z is a subset of the empty set. That was our goal because that's what we need in order to prove that Z is an element of this left-hand side. So then, by axiom 5, which I don't need to mention, therefore Z is an element of the power set of the empty set. And that's it. So that finally proves what we intuitively saw to be true, namely that the power set of an empty bag is a non-empty bag which consists of just one thing in it, which is itself an empty bag.